All right, in this video, we'll be calculating what's called a determinant of a matrix. We'll start with a general 2x2 matrix where the elements are A, B, C, and D, where those can be any real number. And we're going to start reducing this matrix. Notice if I multiply the top row by negative C divided by A and add it to row 2, we'll create a 0 where that C is, right? Because negative C divided by A times A is negative C, and you have negative C plus C. So that'll be our first operation, is replace row 2 with negative C divided by A times row 1 plus row 2, and you'll get this new matrix here. The C turned into a 0, and the D turns into negative B times C divided by A plus D. And that can be written a little nicer by scaling row 2 by A, and you get this new matrix here. And the element in the bottom right of the matrix is now negative BC plus AD. And that number, which we usually write as AD minus BC, is what we call the determinant of a 2x2 matrix. And we have two different notations for the determinant of a matrix A, as DET parentheses A, or you can use bars around the A. Those both mean by convention the determinant of the matrix A. So the determinant of a matrix is just a number. And why is this number important? Well, notice if that number is 0, if the determinant of the matrix is 0, then the bottom row of this 2x2 matrix, when it's reduced, would be a row of zeros. And if you're trying to solve the matrix equation AX equals 0, that is the homogeneous equation, then you'd have an infinite number of solutions. So that's the first important fact about a determinant, is if the determinant of a matrix is 0, then AX equals 0 has an infinite amount of solutions. Right? Imagine the augmented matrix representing the matrix equation AX equals 0. You'd augment the column of zeros as the third column. When you reduce it, you would have a row of zeros for the second row. That means you could write x1 in terms of x2, and you could parameterize it and let x2 be any real number t, and you'd have an infinite number of solutions. And related to this idea is that if the determinant equals 0, then A is not invertible. Okay? This comes directly from AX equaling 0 has an infinite amount of solutions. Right? That means there's not a one-to-one mapping between the vectors that you're multiplying A by in the outputs. Right? AX equals B is not a one-to-one mapping, so there's no inverse that maps B back into X, because AX equals 0 has an infinite number of solutions. All right, let's look at an example of a determinant of a 2x2. If we have the matrix 1, 2, 3, 4, then the determinant of A is AD minus BC, which is 1, 4 minus 2, 3, which is negative 2. That is the determinant of that 2x2 matrix. Right? Nice and quick for that calculation. The determinant of a 3x3 matrix is a bit more complicated. There's not a quick little formula like there is for a 2x2 matrix, but the best way to show you this method is to start straight with an example. All right, so here's this matrix A, and what we're going to do is called a cofactor expansion. And specifically, I'm going to do a cofactor expansion along the first row. And we'll see another example after this to see when it's not along the first row. All right, so what I'm going to do is calculate the determinant of A, and there's our notation. And I'm going to write a plus minus plus, and we'll see kind of a pattern in a little bit. So plus minus plus, and I'm going to circle the first number in the first row, which is a 3. And I'm going to cross off its row and column. And what I'm going to do is do 3 times the determinant of the remaining numbers that aren't crossed off. So 3, 2, 5, negative 1. All right, so that's the first part of our cofactor expansion. Next, I circle the second number in the first row. Right, so I'm doing a cofactor expansion along the first row, so I'm going to stay in the first row here when I circle these numbers. I'm going to cross off its row and column and do the same thing. I'll have 0 times the determinant of the remaining numbers. Right? 2, 2, 0, negative 1. Now that one won't really matter because we're multiplying by 0, so in the end it will be 0. Let's show this, the whole thing here so you can see the pattern. You can kind of guess what we're doing next. I'm going to circle the 4, cross off its row and column, and I'll have 4 times the determinant of the remaining numbers that aren't crossed off, which is 2, 3, 0, 5. So we've reduced this problem to finding 3 different smaller determinants, right? Determinants of 2 by 2 matrices, and we already saw how to calculate determinants of 2 by 2 matrices. So we can do that calculation right here. We have 3 times negative 13 minus 0. Now the determinant being multiplied by that doesn't matter because this is 0. Then we have plus 4 times 10. So that last determinant was 10. And this simplifies to a determinant of the matrix being 1. Now I'm not going to derive why this method works. This that'd take a little while to explain, but this is called a cofactor expansion, and specifically we just did it along the first row. Now, if you didn't want to do it along the first row, but maybe the second row or third row, the only thing that you really have to be careful with is if you're going along an odd row or a column, you could go down a column also, your signs alternate plus, minus, plus, right? So we had plus, minus, plus in this example because we went along an odd row. We went along the first row. So if you also went along the third row, it'd still be plus, minus, plus. If you went along row 2, then it'd switch to minus, plus, minus. So along an even row or column, you have minus, plus, minus is the way the signs alternate. All right, let's work with the same matrix, but this time do a cofactor expansion along the second column. All right, so we're going to calculate determinant of A again. And so this time, since we're going along a even column, we'll have minus, plus, minus. Right? Odd, we have plus, minus, plus. Even, we have minus, plus, minus. And we start with the first element in the second column. So that's the 0. And then we cross off its row and column. And so we do 0 minus the determinant of the remaining numbers. And then we go to the second element in the second column, which is a 3. Cross off its row and column. And we'll do 3 times the determinant of the remaining numbers. And lastly, we circle the 5, cross off its row and column, and do 5 times the determinant of the remaining numbers. All right, so you have to calculate those determinants of 2 by 2s. Right? All you have to do there is AD minus BC, and you'll get this calculation here, which simplifies again to 1. So you get the same answer as we did by going along the first row, right? So if you do along any row or any column, you get the same exact answer. You just have to be careful with your alternating signs. Again, odd row or odd column, you have plus, minus, plus. If you have an even row or even column, you have minus, plus, minus. All right, once you've seen 1 or 2 determinants, you've kind of seen them all. So that's it for this video. Thank you.